again. Good morning and good evening, everyone. I'm Tianshu Hao from Institute of Computing Technology, Chinese Academy of Sciences. Today, I'll introduce you AIBench Scenario, a scenario distilling AI benchmarking. Now, let's start. Let's take a look at the landscape of modern workloads. The emerging modern workloads include big data workloads, machine learning workloads, and internet services like search engine, social network, and e-commerce. Realistic industry scale applications usually contain multiple subsystems, such as online service subsystem and offline analytics subsystem. For each subsystem, there are various modules. Each module serves unique and separate business operations. Within each module, a series of AI and non-AI components are included. In addition, microservice-based architecture have long and complex execution paths containing the whole process from receiving user requests for feeding back results. A microservice-based architecture contains various AI and non-AI modules and consequently forms long and complicated execution paths. Previous AI benchmarking work provides a few macro or component benchmarks and fails to model an industry scale application scenario's overall critical path. So, this figure cited from the following paper illustrates the complexity of a modern end-to-end application. Users send requests over HTTP, which first reach a load balancer implemented with Nginx. Once a specific web server is selected, the latter uses a module to talk to the microservices responsible for composing and displaying posts, as well as microservices for advertisements, search engines. Then we compare the modern workloads with traditional workloads from the perspectives of code size, deployment scale, and execution path. This slide shows the difference of code size. The code sizes of modern workloads and traditional workloads vary by several orders of magnitude. For example, the traditional desktop workloads from Spec 2017 benchmark contains 100,000 lines of code, such as data compression, image manipulation, and the traditional web server workloads like Nginx website contain hundreds of thousands of lines of code. While for modern workloads, the code size usually reaches up to millions of lines of code since they have complex runtime environment stacks such as TensorFlow and Spark and so on. This slide shows their differences from the perspective of deployment scale. For traditional desktop workloads, there are many deployed on a single node. For traditional web server workloads, they are mainly deployed on a small-scale cluster, while for modern workloads, they are mainly deployed on a large-scale cluster that contains tens of thousands of nodes. From the perspective of execution path, modern workloads usually have longer and more complex execution paths than traditional workloads. For example, modern internet service providers pervasively employ AI to augment their services and adopt a microservice-based architecture. Thus, the permutation of several or dozens of microservices constructs the whole life cycle and the critical path of industrial applications. Modern workloads contain diverse modules, complex execution paths, massive scale and complex hierarchy of data center infrastructure. Modern workloads dwarf the traditional one in terms of code size, deployment scale, and execution path. Traditional AI benchmarking methodologies almost adopt macro or component benchmarks, and we will see whether they are sufficient then. For AI macro benchmarks, there is no accuracy information. However, accuracy is one of the most important metrics for AI. Flops is no longer the only metric. Our experiments show that even mixed precision training technology significantly improves flops. However, it may deteriorate the model quality. Only using macro benchmarks cannot find it and may lead to error-prone conclusions. Thus, we think macro benchmark is not sufficient because it has those shortages. No quality information, impact of data input for different layers, no single kernel. Another bottleneck for macro benchmarks is that AI workloads have no single kernel. Through analyzing 17 workloads in AIBench, we find that there are many kernels, so only using one kernel is not enough. Many existing work adopts component benchmarks, which provide a task-level AI model implementation, like image classification. However, our experiments also show its potential misleading. For example, we first benchmark with a single component, image to text. Through model pruning, we find that the tail latency shortens by 51% and the model accuracy decreases 1%, which is acceptable. However, when we put this component into a real scenario and still use the same pruning technology, we find that the tail latency has no improvement, while the accuracy decreases, which is unacceptable. They generate inconsistent conclusion, so only using components may lead to error-prone conclusions. Okay, so we take the e-commerce search intelligence to take experiments and found that the overall system latency indicates that of the entire execution path, including AI and non-AI components. The experiment's results show the overall system tail latency deteriorates dozens or even hundreds of times than a single component. The gap is 2.2 times and 180 times over text classification or recommendation, respectively. When we evaluate a new AI model or accelerator using text classification, suppose it significantly reduces the component tail latency. However, it still contributes little to the overall system tail latency. Therefore, benchmarking a single component cannot reflect the overall system's effects. The online inference module needs to load the trained model and conducts a forward computation to obtain the results. Usually, increasing the depth of a neural network model may improve the model accuracy, but the sad effect is that a larger model size results in long inference time. For e-commerce search intelligence, the model accuracy improvement is 1.5%. We replace ResNet 50 with ResNet 152 in the image classifier. while the overall system 99th percentile latency deteriorates by 9.7 times. So we think benchmarking a single component cannot reflect the trade-off between model accuracy and QoS. Someone may argue that we can use the statistical model to predict the overall system performance, but whether a statistical model can predict the overall system tail latency through profiling many components tail latency performance, our answer is no. We use two state-of-the-art statistical models to estimate the overall system latency and tail latency, a simple queuing model and a sophisticated queuing network model. We find that the gaps between the actual average latency, tail latency, and the theoretical ones are large through the experiments using two scenario benchmarks. For example, for e-commerce search intelligence, the average latency gap is 8.6 times and 4.9 times using the simple queuing model and the queuing network model respectively. And the 99th percentile latency gap is 3.3 times using the simple queuing model due to the non-superposition property of the overall system tail latency being not equal to the sum of each component. The 99th percentile latency is hard to be predicted accurately using a queuing network model. So we do not report the 99th percentile latency gap using the queuing network model. Our experiments using the state-of-the-art statistical models shows that the statistic model cannot predict accurately. There may exist a 3 to 9 times performance gap. The main reason for the huge gap is as follows. It is complex and uncertain to execute an end-to-end benchmark, and the service rate doesn't follow the exponential distribution. So the MM1 model is far away from the realistic situation. However, the more generalized model, such as GG1 model, is difficult to be used to calculate the tail latency. Furthermore, if we try to characterize the permutations of executing dozens of components in an end-to-end benchmark, we need a more sophisticated and analytical model such as queuing network model, which is much infeasible to perform a calculation of tail latency. In conclusion, scenario benchmark is needed. Scenario benchmark is a proxy of a realistic application scenario and a permutation of a series of AI and non-AI components to capture the critical paths and the primary modules. Next, I'll introduce you our AIBench scenario methodology. We conclude the reasons why we need scenario benchmarks because scenario benchmarks reflect the overall system's effects, measure the trade-offs, and it collects different level performance data. And based on this, we propose a scenario distilling benchmarking methodology. We formalized and distilled the real-world application scenarios to an DAG-like permutation of essential AI and non-AI tasks. Then we define the specification and implement the benchmarks. For the scalability and simplicity, we provide a reusing framework to support quickly construction of scenario benchmarks. Through profiling, we identify macro benchmarks. The benchmarks can be deployed on physical machines and simulators. Collaborating with our 17 industry partners whose domains include search engine, e-commerce, social network, a newsfeed, video, and so on, we distill their products or services into 9 representative scenarios, and this figure shows those 9 typical scenarios. E-commerce search intelligence, online translation intelligence, content-based image retrieval, web searching, facial authentication and payment, newsfeed, live streaming, video services, and online gaming. For e-commerce search intelligence, we identify its primary components in this slide. The AI tasks include classification, learning to rank, recommendation, and the non-AI tasks include query parsing, database operation, and indexing. And its data include user data, product data, and query data. And we choose precision, recall, latency as its metrics. And we think the model update frequency is high in this scenario. And for online translation intelligence, we identify text-to-text translation and speech recognition as its AI tasks, and query parsing as its non-AI tasks, and text and speech as its data types. And we choose accuracy and latency as its metrics. And we think model update frequency is low. The next scenario is content-based image retrieval, and its AI tasks include object detection, classification, spatial transformer, and image to text. Its non-AI tasks include query parsing, indexing, and sort. And its data type is image, and its AI and non-AI metrics are precision, recall, and latency. And we think the model update frequency is high. For web searching, we identify its AI tasks are text summarization, learning to rank, and recommendation. And non-AI tasks are query parsing, indexing, crawler, sort, and hash. And its data type is product data and query data. And we choose precision, recall, latency as its metrics. And we think the model update frequency is high. For facial authentication and payment, the AI tasks are face embedding and 3D face recognition. The non-AI tasks are encryption, and the data is face image, and the metrics are accuracy and latency. And the model update frequency is low. For newsfeed, we identify its primary components in this slide. The AI tasks is recommendation, and the non-AI tasks are database operation, sort, basic statistics, and filter. And the data is text. The metrics are precision and recall. The model update frequency is low. For live streaming, the AI tasks are image generation and image to image. The non-AI tasks are video codec and video capture, and the data is image. The metrics is latency. The model update frequency is low. For video services, the AI tasks are image comparison and the video prediction. The non-AI tasks are video codec. The data is video, and the metrics are accuracy and latency. The model update frequency is low. The last scenario is online gaming. The AI tasks are 3D object reconstruction, image generation, and image-to-image. The non-AI tasks are rendering. The data type is imagery. The matrix is latency, and the model update frequency is low. So we distill the scenario stack model into a permutation of essential AI and non-AI tasks and consider it a high-level scenario benchmark specification. Then we propose 6 distinct rules. These rules are our consensus with the industry partners. Through some rules need input from the industry partners. In general, they are generalized, suitable for the other scenarios. Those distinct rules are Rule 1, pruning DAG branches with similar processing logic. Rule 2, pruning the DAG branches with small list fraction. Rule 3, pruning auxiliary functions. Rule 4, using a state-of-the-art AI model. Rule 5, combining the components occurred in successive steps. Rule 6, removing unnecessary components after performing the above 5 rules. So then we take the e-commerce search as an example to explain those 6 rules. For Rule 1, in the recommendation module, personalized recommendation, product recommendation, and advertising have similar processing logic, though they consider different attributes and having different purposes. For example, personalized and product recommendations think user attributes and product attributes respectively. Recommendation cares about the user experience, while as many concerns the click-through rate of advertised products. Here, we only keep personalized recommendation as one essential branch. For Rule 2, within recommender, there are 3 branches according to the query type: image, audio, and text. The audio query occupies the smallest fraction and less than 1%, so we prune it. For Rule 3, e-commerce intelligence focuses on the product searching scenario, so we remove the OLAP analyzer that analyzes the product ordering and the supporting systems, such as monitoring and logging. For Rule 4, a scenario usually provides multiple AI models, which different businesses share. For simplicity, we only reserve one state-of-the-art or state-of-the-practice model for each AI component, like ranker. For Rule 5, we combine the entity identification and the category classifier with recommender, as they both include image classifier and the text classifier. For Rule 6, after pruning the AD branch in the recommender, we remove the AD cluster group in searcher and AD ranking in ranker accordingly. Also, we remove the deduplication component in search planner, as we only need the deduplication in searching the repeated items from the general product cluster and the AD cluster. Besides, indexer only builds the product indexes as searcher focuses on the product attributes to search the product item. Based on those 6 rules, we propose the first reusing framework for easily constructing scenario benchmarks. As shown in this figure, the reusing framework provides loosely coupled modules that are easily configured. It includes the data input, offline training, online inference, non-AI libraries, and deployment tools modules. Based on the reusing framework, we can quickly implement a scenario benchmark. The data input module is responsible for feeding data into the other modules. The offline training and online inference modules are provided to implement a scenario benchmark. The non-AI library module provides non-AI computation and database access, including query parsing, database operation, image and audio pre-processing, indexing, crawler, encryption, basic statistics filter, video codec, and so on. For complex application scenario, the online inference, non-AI libraries, and offline training modules constitute an overall critical path together. The implementation steps of constructing a scenario benchmarks are as follows. Note that the steps are generalized for the construction of all the other scenario benchmarks. First, we choose the essential AI and non-AI component benchmarks from the reusing framework. Next, the permutation of component benchmarks is specified by the scenario benchmark specification. Then we choose the deployment tools such as Ansible and Kubernetes and modify the reusing framework's deployment template. The deployment template includes the module-related configurations, such as input data execution parameters and non-AI libraries. Note that we have provided the default templates on our open source website for both Ansible and Kubernetes. Users can change the configurations according to their environments. Finally, we train the AI models of the selected AI components benchmarks using the offline training module and transfer the trained module to the online inference modules. Note that we also provide a pre-trained model in our website. Then I'll introduce you the AIBench Scenario benchmarks. First, we'll introduce the e-commerce search intelligence. It has 4 parts. The first one, query generator simulates concurrent users and sends queries to online server based on a specific configuration. A query item provides either a text or an image to reflect the different search habits. The configuration designates the parameters like concurrency, querying, arriving rate, distribution, user syncing time, and ratios of text and image items. The configuration simulate different query characteristics and satisfy multiple generation strategies. Query generator is based on JMeter, and the online server receives query requests and performs searching and recommendation, integrating inference consisting of 4 modules. The offline analyzer performs job scheduling, AI model training, and updating. Job scheduler includes batch and streaming lag processing, which updates the models every few hours or seconds accordingly. And the recommender is to analyze query items and provide a personalized recommendation according to the user information obtained from user database. And the data storage module stores the data. And for online translation intelligence, we also have several parts. The query generator simulates concurrent users and sends either a text, an image, or audio to online server. The configuration information is the same as that of e-commerce intelligence. The online server contains 4 modules. Search Planner is the entrance of the online server, which also uses the Spring Boot framework. The image converter receives an image query and extracts the text information within the image. It first performs image pre-processing using a basic 64 image encoder, since the RESTful API requires encoding binary inputs as base 64. And the text translator performs translations and reuses the text-to-text translation component. The offline analyzer performs job scheduling, which is similar to that of e-commerce intelligence, except that they use different AI component benchmarks and update intervals. Our methodology provides a 2-level mechanism to verify whether a scenario benchmark can represent the real-world application scenario. On the specification level, it is much easier to validate whether the scenario benchmark's specification captures the essential parts of a scenario, as we can easily reach a consensus about the efficiency of the distilling rules with the industry partners' feedback. On the implementation level validation, we compare the scenario benchmark with the real-world scenario from the perspectives of both overall system performance and single component performance. From the overall system performance perspective, we compare the overall system latency of the whole execution path under the same deployment. We define their deviation as the ratio of absolute latency difference between a scenario benchmark and a real-world benchmark. Now, let me show you some our experimental results. In our experiments, the online server of e-commerce intelligence and translation is deployed on a 50-node CPU cluster and a 5-node CPU clusters, respectively. We deploy their offline trainers on GPUs. These experiments demonstrate how to drill down from a scenario benchmark into individual modules or even primary components for latency breakdown. This explains why a statistical model cannot predict the overall system tail latency and characterize the microarchitecture behaviors. The overall system latency indicates that the entire execution path, including AI and non-AI components. Our experiments show the overall system tail latency deteriorates dozens or even hundreds of times than a single component. The gap is 2.2 times 180 times over text classification or recommendation, respectively. When we evaluate a new model or accelerator using text classification, suppose it significantly reduces the component tail latency. However, it still contributes little to the overall system tail latency. We also analyze the execution time ratio of the AI components versus non-AI components of the overall system latency. If we exclude the communication latency, the average time spent on the AI and the non-AI components is 137.12 and 58.16 milliseconds for e-commerce intelligence, while for translation intelligence, nearly 99% execution time is spent on the AI components. This observation indicates that the AI components contributions to the overall system performance vary from different scenarios. Reproducibility is of great significance for a benchmark. We repeat 2 scenario benchmarks 5 times to verify their reproducibility. We use the coefficient of variation called CV as the metric, which is the standard deviation ratio to the mean value. For e-commerce intelligence, the CV for the average 19th percentile and the 99th percentile latency is as follow. Respectively, for translation intelligence, the value is as follow. The experiments show that our scenario benchmarks have extremely low variance. We run the recommendation component both within e-commerce intelligence and the real-world scenarios to compare a single component's performance. We choose recommendation as it is the most time-consuming component and impacts the overall system latency significantly. The average latency of recommendation for e-commerce intelligence and real-world scenario are 97 and 103 milliseconds respectively. And the deviation is 6%. For the CPU utilization and the instructions per cycle, the values are 51% versus 50%, and O.59 versus O.6 respectively. The deviations are 2% and 1.7% for CPU utilization and IPC. Thus, from a single component level, our benchmark still reflects its importance on the critical path and reflects similar workload behaviors within the real-world scenario. As our many industry partners release, they have to update the AI models in a real-time manner using an AI model for an online service. For example, one e-commerce giant demands that the AI models are updated every 1 hour, and the updated model will bring in the award of about 3% click-through rate and millions of profits. Our evaluation shows offline training should be included in scenario benchmarking as it is essential to balance the trade-offs among model update intervals, training overheads, and accuracy improvements. Updating AI models in a real-time manner is a significant industrial concern in many scenarios shown. We evaluate how to balance the trade-off among model update intervals, training overheads, and accuracy improvements using AI offline trainer of e-commerce intelligence on the Titan XP GPUs. We reset the input data volume to investigate how to balance trade-offs among models, update intervals, training overheads, and accuracy improvements. For image classifier, 51 additional training time brings 4.96% accuracy improvement. And for ranker, for ranker from 60% to 100%, 70% additional training time brings 1.36% accuracy improvements. And for different AI components, the trade-offs have subtle differences. This presentation introduces the challenges of characterizing modern workloads, the AIBench websites, testbed, and the latest technical report are published available from the next page. Also, the FIDSS challenge in bench consoles will on benchmarking AI and other emerging workloads. And we propose the reusing framework to scenario and implement two scenario benchmarks. This page introduces our reference and publications. You can visit this website. Thank you for your listening.